In this module, we're going to look at how we use moles to calculate formulae, and we're going to look at both empirical and molecular formulae. So let's have a look at empirical formula. So this shows the simplest whole number ratio of each element present. So for example, when we were working out the formula of calcium oxide, we first of all came up with the formula of Ca2O2, but then we cancelled that down to give us CaO, which is of course the simplest ratio. When you think of what is actually happening in an ionic compound, you have billions of calcium 2 plus ions in a lattice with oxide ions. So we, rather than actually say how many are in that solid, we just say what's the ratio between them, and we know that for every calcium ion in the compound, we will have one oxide ion in the compound. So here are some examples of empirical formulae. Obviously the first two are ionic compounds, and those last two are organic compounds. And you can see that we have a formula of CH2 and also CH, and we know that can't be the actual formula, the actual atoms that are in the molecule, because we know carbon forms 4 bonds. So the molecular formula sorts that out for that, and that shows us the actual number of atoms of each element present in the molecule. So rather than saying the formula is CH2, that's my empirical formula, which is the simplest ratio, the molecule is actually containing 2 carbons and 4 hydrogens. But you can see how, if we wanted to cancel that down, it could become 1 to 2, as we have there for the empirical formula. And the same here, the empirical is CH, but actually in each molecule there is 6 carbons and 6 hydrogen atoms. So this here is the molecular formula. That is actually the number of atoms in each molecule. So let's have a look at how we can use moles to find out the formula of a compound from experimental data. So best way to do this is to do an example. So let's say we've been given a compound. It contains chlorine and iron, and we've been told the mass of chlorine and iron in the compound. And as you know, as chemists, we can never compare mass to make a fair comparison. Because we need to compare the number of atoms of each in the compound, we need to convert our grams into moles. So how do we do that? Well, we divide by the molar mass. So let's do this. And the easiest way I find to do it is to do it as a column. So we know we've got iron and chlorine. Put the masses down, and then we divide those masses by the molar mass of iron and the molar mass of chlorine respectively. And that will give us the number of moles. So we know that for every mole of iron, for every 0.0633 moles of iron, we have 0.189 moles of chlorine. And obviously we don't want to write the formula like that. That wouldn't make sense at all. We need a whole number ratio. And the easiest way to do that is divide by the smallest number in the ratio. Our smallest number in the ratio is, of course, the iron. So we do that for both, and we will end up with the following ratio. So we obviously, iron will become 1, and 0.189 divided by 0.0633 becomes 3. So therefore our empirical formula is FeCl3. So here's another example for us to get our teeth into. Now we have 3 elements in our compound, carbon, hydrogen and nitrogen, but we go through exactly the same process. So let's put them in a little table there. Carbon, hydrogen, nitrogen. Put the mass in that we have for each, and we divide each by the respective molar mass, and that gives us that ratio there between carbon, hydrogen and nitrogen. Again, we couldn't put that in the formula. We'd need to divide by the smallest number. The smallest number is going to be 2.22 in this case. So we will do that, and when we do that, we will end up with the ratio of 2 to 7 to 1. So our formula is C2H7N. Now, you'll be pleased to hear it's relatively straightforward to extend those ideas to find the molecular formula. So let's do that. So we'll work out the empirical formula first for this one, and then find the molecular formula. So again, let's put those numbers in a table for carbon, hydrogen, nitrogen. We've got the masses there, and we divide by the molar mass of each to find this ratio. Divide by the smallest one, and we will end up with the ratio of 1 to 2 to 1. So the empirical formula is CH2O. However, they've given us some additional information in this question. They have actually told us the molar mass of the compound. If we add up the molar mass of CH2O, this comes to 30 because it's 12 plus 2 plus 16. And of course, that's only half what it should be. So the way we need to deal with that is to find a molecular formula. We times that by 2 to give us the molecular formula of C2H4O2. So it's over to you now to have a go at doing some questions. So we've got 3 questions there to have a go at looking at empirical and molecular formulae. If you need a little bit of help, there are some hints coming up now. So here's some hints for you. For the first one, we have been given NH2 as the empirical formula here, but they've told us the molar mass is 32. If you work out the molar mass of NH2, that's going to be 14 plus 2, which is 16, which is only half of 32, so we need to multiply the formula by 2. For number 2, the way to do this one, a little hint is, remember, the first thing you have to do is work out the number of moles of each of these and then find your whole number ratio. Number 3, exactly the same way, but work out your empirical formula first and then look at working out your molecular formula. So the answers are coming up now. So hopefully you got the answers all okay. So for B, you needed to multiply the formula by 2, and for C, you need to multiply it by 6. The empirical formula for number 2, if you work through the system that we've used, you get it to be Na2S2O3. For 2B, you should have found it to be NO2. And for question 3, you work out, again, exactly the same way, divide by the molar mass of phosphorus and for oxygen, the relative percentages, and you will end up with the formula of P2O3, but that has a molar mass of 110. They've told us that it actually has a molar mass of 220, so you have to times it by 2 to get your molecular formula of P4O6. You've noticed, I imagine, that they've given you percentages rather than grams. It doesn't matter at all. You can easily just pretend if I had 100 grams of this compound, 54.6 grams would be phosphorus and 43.6 grams would be oxygen. So it doesn't matter if they give you percentages, just use it in exactly the same way. So some of these slides can be downloaded from the website, and hopefully you found that useful. A little bit of practice of working out empirical and molecular formulae.